So we're going to have a joint session here. So first of all, I'm going to be talking about what PTC's been doing on the Creo side, and then Luke from the Answers team is going to talk about the tools that Answers have in terms of simulation of the additive process, how to ensure you get best print results from complex printing. Some nice, very nice little tools inside there. Okay. All right. So on the talking about additive manufacturing, the design for additive manufacturing. So, you know, in terms of Creo and the history for additive manufacturing, so those capabilities were first introduced in Creo 3, where we saw direct 3D printer support for some of the Stratasys printers, so you could go directly from Creo straight into that printer. So that lets you do things like, you know, looking at support material, calculating build times, you know, to apply surface finishes, validate your geometry. Okay. So some basic, basic tools inside there. So that was expanded in Creo 4. So more printer support. So they also started supporting direct connection to some of the 3D systems printers as well. Okay. The new option for print tray assembly, so you could build up an assembly to send that straight off to your printer. The big one was the introduction of the Lattice feature. Okay. So who has got 3D prototypes printed here? Okay. Who's 3D printing production parts that actually go onto the finished product? Only a couple. Okay. So typically, you know, when you're printing a prototype, you know, you're looking out for size and things like that. So a lot of the software that comes with the printer has the options, you know, hollow it out and fill that in with some sort of lattice structure inside it. Okay, to speed up the print time, less material being used. Okay. But as we move more towards additive manufacturing, you know, Alan from PTC showed some of the examples there. We're starting to get these very complicated shapes and designs. Well, if we're using all these lattices in a production part, you know, how do we know that that's going to be strong enough? All right, if we're going to take that out to the printer software and turn it into a lattice. So PTC introduced the lattice feature inside Creo 4 to let us build that into the design part so that we can validate the geometry. Okay, because it's no longer just something you do for speeding up the print. It's actually part of the geometry that you're actually manufacturing. Okay, so that was introduced inside Creo 4. In Creo 5, more printer support, so moving more into the online bureaus, that are becoming a lot more popular. Also introducing support for metal printers as well. Okay. So in Creo 6, there's been a whole bunch of enhancements on the additive side. Okay, so covering performance, new options for placement, shape, printability, materials, and connectivity. Okay. So performance enhancement. So now we can build these lattice features. We can have very, very big, complicated lattices with lots of bits inside it. So they've done again a lot of back-end tweaking for the engine to make that regenerate faster. So some examples. I've done some testing myself and to see, and you know, with similar results. So this part here, turn that solid part into a lattice. In Creo 5 took 137 seconds. In Creo 6 it takes 6 seconds. Okay, so some pretty significant performance improvements there for generating lattices. Okay. Build direction. So build direction is very important when you're printing a part. Okay. So Creo in 6 they've added some new options for basic geometry checking of your build. So for things like minimizing the height or minimizing the amount of support material that you might need. Luke's going to talk about some very cool Answers tools that they have around the analysis of that process and stresses that might leave in. Probably the biggest thing is the new shapes. Okay, so inside our lattices we've had our 2.5D and 3D lattices. Okay, so there's a whole bunch more lattices been introduced. So stochastic lattices. Okay, so these are essentially beam-based non-uniform lattices. Okay, so it's sort of foam type lattices. Basically good for filling in areas, like if you've got a skin that you're trying to fill in between, you don't want some even pattern, you want some sort of bit more random to give you better strength. Or great for, you know, they use quite commonly in medical implants, where you want some sort of rough organic shape that bone and muscle and things can start to embed into. Okay, so that's a new stochastic lattice that's been introduced. Some new formula-driven cell types. So these come out of a lot of research that's being done into different structures for additive manufacturing. So these are the new triply periodic repeating structures. So the idea of these are that they are self-supporting, so they don't need support material while they're being printed. They're also designed to handle different load cases and scenarios. Okay, so So three new types inside Creo: gyroid, primitive, and diamond shapes that we can generate as well. Okay. And also, if you don't like any of those options, you can just model your own lattice. Okay. So you can basically create your own part. As long as it meets the certain conditions, like it's got to be a B-rep, it's got to fit inside a cube, you should make the opposite sections match up so when you pattern it across it doesn't have some weird offset. But basically you can model whatever your part you like and that can be your lattice. So you can go nuts, okay? Alright. Some new options for transitions. So basically if you're dealing with supported walls, how we can handle the transition of that while we're printing to give better support. Homogenization. So sometimes you might want to create a really, really dense lattice, which yes, it's fast from Creo 6, but some of the options might still take a while. So rather than modeling the lattice, you can actually model it as a homogenized material. So it essentially creates a solid that has the same physical properties as that lattice would have. Okay. On the connectivity side of things, okay, so 3MF support, okay, 3MF export. So most of you who are doing 3D printing have probably dealt with STL files, right? That's pretty much the old standard. STL files, you know, your faceted triangulated data, but STL file, this is a lot of information. Things like, you know, material definition, color definition as we move more towards more advanced printers, okay? So 3MF is a file format that was developed by basically an industry group. PTC was one of the founding members of that, to define a new file format that will support the future of 3D printing. So it has a lot more advanced options than STL files used to have. So things like colors and different lattice types and all that sort of stuff, material definition and everything else. So in Creo 6 now we have support for materials and colors and lattices inside 3MF files. Okay. Also new CLI format, which is widely used by metal printers. They like to sort of send off a slice to the printer, have it process that, and then send off another slice later on. So more support there on the metal printing side. Okay, so that's a little bit of a look at some of the enhancements in the additive side. So just to show what some of those things look like, let's just open up. So this is the lattice feature that was introduced back in Creo 4. So all that there is one feature. Okay, if we just edit the definition of that, that's our lattice. So we said we're going to put a 2.5D lattice. We're going to use a hexagonal shape. We're going to fill in those two areas there. Okay, so we've got all of our different cell types. You know, triangular, hexagonal, square, octagonal. Okay, so we can see all of those sorts of different shapes there, like so. All right. So we've been able to do that since Creo 4. Now we can go back in and maybe choose beams. Okay, so this is our 3D shape now. Okay, so we just need to change the sizes of these. 2 and 0. Okay, so we've got similar things again. We've got our hexagonal, square, triangular shapes, octagonal shapes, like so, that we can fill in with a 3D lattice. Okay, so we've been able to do that since Creo 4. Okay, so what's new now is the new stochastic option. Okay, so this is creating a more randomized kind of shape. Okay, so it's using beam elements. We can say target cell size. So there's one cell of that. So let's drop that down like 15, like so. So what that's going to give us is this kind of irregular fill inside that area, like so. So we can say that based on, you know, a cell size. Or we could say it based on a number of cells that we want to have inside it. Okay. So we can also have the option there to randomize that as well. So that's the new stochastic option. The other option I mentioned was the new formula driven. Okay. So with that formula driven, again, if we look down in here, let's just make that a bit bigger and change the wall thickness of that. Okay. So there's our new shape. So we've got our gyroid or primitive or diamond shapes as well. Okay, so we can use them to fill in that area. Like so. Okay, so that's some of the new options that are there in the lattice feature inside Creo 6. All right. All right, and the other part is topology optimization. Okay, so as Alan from PTC talked about this morning, you know, PTC had a new acquisition late last year called Frustrum. which is looking at AI-based generative design. Okay, so we're going to see a bit more of that coming out over the next year. Topology optimization, like this was first level 1 that Alan was talking about, that's been available since Creo 5, it was when it first introduced. So in Creo 6, a few more expansions of that. The ability to support assemblies with topology optimization, some new options around basically making viewing those results a lot quicker and easier. So really Creo's big party trick, if you like, on the topology optimization side was the ability to very quickly create a manufacturable part from that. So typically you'll take your part out of CAD, you've got a whole bunch of lovely NURB surfaces, you'll take that into your optimization tool, which will give you this lovely faceted model, and now you've got to try and work out how do I bring that back into CAD and turn it into a surface again. Okay? So in Creo, when that was introduced in Creo, there was the geometry reconstruction option, which uses the freestyle feature to build that. So a few more enhancements to that. So the ability now to basically control the level of detail to better match that topology mesh that gets built. Some new options for editing and cleaning up those facets as well, to smoothing them out if you need to. And also the ability to reconstruct from facets like further down the track rather than having to do it at that point in time. Okay. So just to show you what I mean by that, if we let's open up my part. So I've got a part here. And I've already run the topology optimization, so it takes a little while to run. So this is basically, I ran it based on, you can see the loads being applied there. There are some manufacturing constraints on there as well. We're looking to minimize mass on that as well. Okay, so we've got that. Here's all these conditions, so come up with some geometry for me. Okay, so I ran that on my machine. It took about 15 minutes to run, so we don't want to sit here and wait for that to happen. But essentially gives me that's the resulting geometry that meets those conditions, right? So this is like typically what a topology tool will give you, okay? So I could just say okay to that and now get a test-loaded model. But what I can do is I can say, well, give me a geometry reconstruction. Let's go to level 3, okay? So it will now automatically build for me a surface to match that facet, okay? So it's using the freestyle feature that was introduced back inside Creo 1. Which is essentially that, fully free-form shape, great for building sort of organic shapes, complicated geometry. So it's now building that the facet. Now you can see it's building the freestyle feature to match up to that facet geometry. Okay, and what I'll end up with is essentially the finished part. Okay, I can now run toolpaths off, build it, whatever I need to do. Okay, so there's my finished surface model.
So
Solid
if you
part.
do it for that topology, why can't you do it for scan data?
So you now can. Okay, that was that last slide that I talked about. Okay, you need to have Rex or topology optimization to do it, but it can do it. Yeah. Okay. So I've got options. I can see here where I've put a bit of a kink in because of the way the mesh was and what I was trying to do. So I could go back and edit the facet if I need to. Okay, so maybe I need to refine that facet a little bit more. So I've now got tools inside there for my different sections of the facet that are built. So maybe I could refine that and subdivide that down more, okay, to get a smoother mesh. Or maybe I might go into the freestyle feature. Okay, and you can see this is what Creo built automatically is that surface. Okay, so you could manually build that if you really felt like it. Okay, but I'd much rather the system do that for me. Okay, so that's what it builds. So I can go into these, you can see where that fold is, okay? So on that primitive there, I could maybe go and reconstruct that again from the facets. Maybe let's just go level 2 this time, to maybe try and smooth that out a little bit more, okay? Like so. And there's my finished part, okay? So much simpler process for getting from that optimized facet geometry back into something that's a bit more manufacturable, okay, and usable in CAD. All right. Because the important thing is that topology optimization doesn't always have to be about additive manufacturing. The constraints you can apply, they might be, I've got to be able to cast this or forge this. Okay. So you've got a model like that, you need to be able to have surfaces to your splits for your mold and tooling and everything else as well. Okay. So that's what Creo offers in terms of that one-click ability to create that geometry. Okay. All right. So that's that's from my side on Creo. Okay, so a lot of tools there on the design side of additive manufacturing. So I'm going to hand over to Luke now, and Luke's going to talk about all of the lovely little tools that ANSYS has on the I guess manufacturing process simulation of additive manufacturing.
Okay, so I have here for a very short period, about 10 minutes I think, before we have a couple of customer presentations. This is just a short section on the additive printing tools in ANSYS. So we have three tools, basically. There's the ANSYS mechanical-based simulation tool for simulating the additive manufacturing process. Then we have additive print and additive science. So basically I'll be explaining what these tools do and introducing some of the new features in 2019 R2. Right, so at the moment ANSYS is really focusing on powder bed fusion additive manufacturing. So this is where we have a layer of powder and then a laser melts the powder and forms a layer of metal, and then a wiper runs over the top, as you can see, and adds another layer of powder, and then the laser melts the next layer. And basically we build up our part by repeating this process, and eventually you get something like this, and you just pull it out of the powder. So that's what, as I said, that's what ANSYS is focusing on. In the future, there will also have polymer-based additive manufacturing. That's what we have at the moment. Essentially, the fundamentals are the same when we're thinking about residual stresses and strains and those sorts of things. So these are some of the concerns that we can have with additive manufacturing. So in this case, we've had some shrinkage effects that have introduced residual stresses, and it's caused cracking in the part and between the part and the base. So you can see this crack moving through the part here, and also it's cracked away from the base. We can also have dimensional problems. So due to non-uniform shrinkage of the part, you can get dimensional instabilities and inaccuracies in your print. And in this one here, we can see it's broken away from the supports. So this is just support material that we would cut away after the print, but it's broken away in this state, in this example. And down here you can see more cracks in the part due to thermal shrinkage. And then there's also the question of the metallurgy of the part, because essentially we're taking powder and we're melting it with a laser, and that's developing the local metallurgy, which will affect the material properties. So our whole process affects the resulting strength and durability of the material and the part. Traditionally, without simulation tools to look at this process, you would have to use a trial and error process to get this right. So you might print this part this way up, but you find you get some residual stresses that cause some cracking, or the dimensional stability is not very good, so we try printing it upside down, or print it 90 degrees from that orientation. It's basically trial and error. You may vary the laser power or the scan speed of the laser. So the idea behind these predictive tools is to minimize the amount of wastage, because these take hours to print, sometimes days, and you don't want to have to do this too many times. Prefer to get it right with simulation first, and then just hopefully print one part. So we start out with a powder, and we run a thermal process over it, probably with a laser, and that melts the powder, and then that solidifies and gives us some sort of microstructure, and that gives us our resulting mechanical properties. But a designer thinks in the opposite direction, so they start out with some mechanical properties that they would like to use or have for their design, and they'd like to know what process they require to get those mechanical properties. So simulation helps with that as well. So that's more focused on the additive science tool that I'll be introducing a little bit later. So one of the things that these ANSYS tools do is they can take the scan patterns from a particular printing machine. So here we have a bunch of printing machines. All the printing machines have their own particular scan patterns. So these are some scan patterns that you see. Basically, it's the pattern that the laser follows to melt the powder. And if you want to get an accurate thermal history of the printing process, like you can see here on the right, you need to know, is this the problem that was...
I've been doing it all morning, I don't know
why. What's the magic trick?
Tap on the buttons on here, and it just decides to come back. Just
all displays. What if I unplug and plug back in? We've got a different thing. It's back. Just, yeah, so don't touch anything. Cool. Okay, so to get an accurate residual stress prediction and deformation prediction, you need to know what the true thermal history of the part is during the printing process. So by having this information and applying it to the print process, we can get this sort of simulation, and it gives us a much better prediction of strain magnitudes, defect distributions, the local microstructure of the material, and the resulting mechanical properties. Right, so topology optimization is 3D printing's best friend, really. They really go hand in hand because topology optimization makes these amazing organic looking parts, but they're not really manufacturable with anything but 3D printing, unless we apply manufacturing constraints. And we can do that in the ANSYS tools. If we want to do injection molding or casting or something like that, we can basically tell through the topology optimization tool that that's what we want to do, and it'll only produce a part that is manufacturable with that process. But in the ANSYS the ANSYS topology optimization, we have a new tool for lattice optimization. So this is a bit different to what we're looking at in some of the earlier presentations with topology optimization. So this allows us to take our part, our bracket, we run a lattice density optimization, like you can see here, and you can more or less see the load path. So this is the red regions are where we really need the material to maintain strength in this part, and the blue regions are where we can save some weight. So we do this lattice-based topology optimization. We send that off to spaceplane, and it gives us a non-uniform lattice density distribution. So you can see in the areas where we don't need so much strength, we can have thinner members in the lattice, and where we do need lots of strength, we can have thicker members in the lattice. So it gives us the same shape, but a non-uniform lattice density distribution allows us to save as much weight as possible. And then you can go and 3D print that. Okay, in spaceplane we have a new tool for designing the supports. So for something like this hip implant, we can't really just lie it on the bed and print it. So we need to have supports, as you can see here. So additive prep in spaceplane allows us to design these supports, but it also allows us to optimize the orientation of the part to minimize the amount of wastage of the material. So these supports they're printed in the same material as the base structure, but then they're cut away and thrown away. So they're cut off and thrown away. So we want to minimize that wastage. So this additive prep tool will work out an orientation for our part that will minimize that wastage. Okay, so this is the mechanical additive manufacturing tool, or it was. That's right. In ANSYS Mechanical. So this is a tool for simulating the printing process, and it gives us an animation of the printing, obviously. And on the left we have the thermal results, so you can see where the laser has most recently been, is the hottest region. Then we have the thermally induced distortions, and then on the far right we have an animation of the residual stresses.
So what's the size of your mesh? Is it microns or is it millimeters? Is it?
No, it's in millimeters range. Yeah. So you can see the mesh in this slide. So that's the sort of size of the mesh. So because it's a layer by layer structure, or layer by layer process, we need a mesh that allows us to simulate that. So a Cartesian mesh, like this one that you see here, is a perfect candidate for 3D printing.
But each layer is about 50 microns, but if you are assuming the mesh is in millimeters, you are
yeah,
approximating.
each layer of mesh represents a multiple,
about
10
layers.
Yeah, yeah. So the downside of this Cartesian mesh is it tends to de-feature small features like small holes or radii regions, and it gives a not imperfect prediction of residual stresses. So we have a new layered meshing method that you can see here on the right. So this has come out in R2, I think. As you can see, it's still a layered mesh, but it uses tetrahedral elements. So in the regions where we have small rounds and other smaller features, we can better capture those features. So we get a better prediction of the residual stresses using this layered mesh. And we can also simulate a heat treatment step after the printing. So here we have a little test case. We've printed these two parts. And then in this case here, we've cut off the supports, and then due to the thermally induced residual stresses, we've got this deflection that occurs. But if we apply heat treatment steps before we remove the supports, we get less deflection. So we can simulate that process now and get a prediction of how much deflection you get from the part. A couple of other things. We can utilize the part transform feature that I was talking about earlier. If you saw my mechanical presentation, that allows us to run multiple simulations of the printing process in different orientations for the part, so we can see how different orientations affect the result. And we can take advantage of symmetry if the printed part is symmetric. Now we can also include the powder in the print. So this is the part that we want to print, but in reality this is still embedded in powder, and temperature will be transmitted through the powder. So we want to include the powder in the printing simulation. So we can do that. So that's what we have on the right hand side here. The powder is still in there, and the thermal effects due to the presence of the powder is incorporated in the simulation. And we can also include clamps, thermocouples, and all that other stuff that is included in the machine during the printing process. And then finally, this is a problem that can occur with this type of 3D printing, where distortions in the part due to thermal stresses can actually cause the part to deform during the printing process and then lift out of the powder bed. And if it lifts too far out of the powder bed, that wiper that adds the next layer of powder can collide with the part. And that will obviously damage the part, and it'll damage the machine as well, so you end up with downtime. So this tool will predict any of these collisions that can occur, so you can then change the process to minimize collisions. Right, so that was the ANSYS mechanical-based additive print tool. So this is a different additive print tool. So this is intended for doing for producing a compensated design to minimize the effects of thermal distortions. So this is a little filter. The filter's about this big, and this is the design that we want to produce. But if we go and print that, you can see we end up with these bulges here, these distortions. So this is the actual printed part. So it doesn't exactly match the part that we wanted to make. So additive print will produce a compensated design. So you can see the compensated design here. So it says, right, if you print this, you will get what you want. So then we go and print it or run the simulation, and you get something that is much closer to the intended design. So it's basically calculating a compensated design for our print. So I'll just let that run to completion. Cool. Okay, so there's a couple of updates in R2. One of them is the new voxelization process. So this uses a concept called voxels instead of elements, like I was referring to earlier. So where these voxels are too large for small features in your geometry, you can split the voxels into sub-voxels. So here we used a sample rate of 5, and it splits this one large voxel into 125 smaller voxels to better capture smaller features. And you can also upload your own supports for the printing process. Previously, you could either print it with no supports, or you could ask it to produce its own optimized supports. But now if you produce a support design in SpaceClaim, for example, you can upload that STL file and use that.
Sorry, are those voxels treated as elements in the solver, or?
They treat it as elements.
Yeah.
They're more like a sort of an Euler representation, where they can have a combination of material or void. So it's not quite the same as an element. Okay, so then finally there's additive science. So additive science is a tool that we use for predicting the microstructure and the material properties. So you can see there's a little DOE that's been done here, and they've run a couple of scan speeds, so from 500 millimeters per second up to 1200 millimeters per second, and a range of laser powers from 50 watts up to 195 watts. So you can see if your laser is underpowered and you run the scan speed too fast, you get this balding effect or beading effect. It basically just melts the top layer of powder, and we end up with loose beads, so it doesn't penetrate. But if we crank up the laser power so it's too hot, it melts the layers below the powder as well, and we can end up with voids, or what they call keyhole effects, in the material. So we want to be operating the printer somewhere around here, where we can get a good quality print at a reasonable output rate. So this is these are basically the same parameters, but they printed the part and cut the material open to have a look at what's inside. You can see here the material hasn't really fused at all at this low power rating, but then at this high power rating, here there's little keyhole voids. And as you can see here, this is some nicely solidified material. So additive science basically does the simulation of a single scan, and then it does a prediction for the optimum process parameters. So this is the layer of powder, and then there's the underlying layer of material that was laid previously, and then we have the laser. So it will give you some sort of prediction of where our optimum Goldilocks zone is for our process. So here we have our laser power and then our scanning velocity. If we run the printer at too low a power, we get a lack of fusion, especially at higher velocities. If the power is too high, we get keyhole formulation, but somewhere in here we get a good process. So you can see what these look like. So there's the keyhole formulation, there's the balling up. So a machine manufacturer will typically tell you to operate your machine somewhere in here. So there's your point, to run your machine at that process parameter, and all will be well. But you could possibly run it a little bit faster, run it at higher scanning velocity, and get a faster print, so you get higher output. So additive science will be able to tell you that. Like, what are the actual limitations of your printing process? Can we run the machine a little bit faster and still get good parts? So you end up with a plot like this. So these blue dots are where the melt pool is too deep. Yellow dots are where the melt pool is not deep enough. And then we have our happy green points here where we can operate our machine and get a successful print. We can also do optimization studies to minimize porosity in the part. So we can run multiple permutations, up to 300 permutations, to minimize the porosity. So here's an example of that. So they've run over a bunch of different scan speeds, layer thicknesses, hatching spacing, slicing stripe width. And this gives us a solid ratio. So we want a solid ratio as close to 1 as possible. So in this case, the hatch spacing, which is the distance between the laser scans, is affecting the solid ratio here. So at higher than 0.09 millimeters, the porosity, the solid ratio starts to drop off very quickly.